Well, thanks so much to the organizers for inviting me to this wonderful conference and wonderful, beautiful city. And thanks to everybody for attending, and thanks to all of you for making it such a wonderful experience and conference. Yeah, so pseudo-intersections and a variant of matrix forcing. Probably the highlight will be maybe this variant of matrix forcing, but I want to do a bit of background. I've been interested in pseudo-intersections for a very long time. Oh, I meant to change that joke to P or not P rather than to P or not to P. I thought that one was even too juvenile for me, but okay. All right, so it's already been mentioned by Marlena, the Balcar-Simon-Pelant beautiful theorem, 1980. I didn't yet have a PhD at that time, got it that year. So that the power set of omega mod phin has a, what I think of, they didn't say it this way, they said base matrix, a dense tree of height h, and they showed that the cardinal invariant h, the distributivity number is bounded above by the minimum of B and S. And always topologically, that's where I think the original interest in this result was, that N star has a high base order type of a tree of height h. And they also showed that it was independent whether or not this tree necessarily had cofinal branches. So I think that pretty much summarizes, not everything they had in that great paper, but lots. I just already mentioned to Marlene about this question I raised a number of years ago. It's obvious that if the pseudo-intersection number is the continuum, then that tree has to have tree type complete C-ary tree of height C. And I always wondered if the converse was true. I just tossed that out there. And in the early days, 1980, 81, 82, people like Van Douwen, Van Mil, me, many others working in stone check compactifications, we couldn't tell N star apart from any other space. They all looked the same. Probachenko's theorem characterized all these spaces under CH. Every stone check remainder of a locally compact, sigma compact, zero-dimensional space of weight less or equal to continuum. They're all homeomorphic. So as I said, they all looked like N star, especially before Saharan's result came along. For example, if you puncture the Cantor set and then take the stone check remainder, that's a copy of N star under CH. We know very well it's not homeomorphic. To me, another fundamental subspace still to this day, because of questions in Banach spaces, the boundary of a co-zero set, that's what that is to me. A non-Clopin co-zero set, so an increasing chain of countable increasing chain of Clopin sets, and you take the, well, that's a space whose stone check remainder is a copy of N star, and that's what the boundary is in N star. You can think of that as power set of omega mod fin cross fin, omega cross fin cross fin. And I just wanted to mention this beautiful result in the early days by Andrei Szymanski. He noticed that in ZFC, that structure, the one that under CH is exact copy of N star, it never has allophone closed dense subtree. So that was kind of really interesting. And so they're, so not having allophone closed is very connected to pseudo-intersection numbers. And then let's move on to more recent results, which a lot of these have been mentioned, the Mathias forcing, I don't know, Mathias or I think Booth also can take credit for this forcing where you have a filter and you add a pseudo-intersection to the filter. So that would be the one where the side conditions, you have a finite initial segment, side condition and another side condition member of the filter. And even better for many results, as others, Jorgen, Michael Rushak, and many others have noticed, is if you do laverize it, so the full F branching tree. So both of those forcings add a pseudo-intersection to the filter, but what makes them special is possible preservation properties. And then, of course, everybody knows the Mathias model is the countable support iteration of Mathias forcing which could be regarded, as Marlena mentioned, force with the power set of omega mod fin, and then add the generic ultrafilter, and then diagonalize the generic ultrafilter. So the Mathias model has been interesting to P omega mod fin, and topologically for a long time. I'm attributing this to 3 authors, but it's originally just Baumgartner and his student Dordel. Now, they didn't really show in the Mathias model because they didn't have Shelah's proper forcing iteration technology at the time. They used modified support Mathias model, and they proved that the distributivity number for P omega mod fin was omega 2 in that model, and that there are no omega 2 towers. And then, of course, with Saharan's preservation results, you can just go to the full Mathias model. And so that shows you a big difference, right? So the pseudo-intersection number, H is omega 2, and not only is the pseudo-intersection number omega 1, but you just can't find an omega 2 length tower. That's interesting. Even before all of this, in fact, my PhD supervisor wrote a book called Absolutes in Topology. So he was very, very interested in this notion of absolute. There's a Gleason, Andrew Gleason initially talked about it topologically, but you can look at it set theoretically. You take a topological space, preferably regular, and you take the Boolean algebra, complete Boolean algebra of regular open sets, and two spaces are said to be co-absolute if they have the same regular open algebra. Wiscomfort, Stelios, Negroponte looked at the structure of omega star before Balcar, Pelant, Simone's result. And so anyway, I was certainly interested in that for a while, and had to proofread my supervisor's book. And so I proved in the Mathias model that this space, now of course that's the real line, but in terms of co-absoluteness, it's the same as the Cantor set punctured a point. There's zero dimensionality, doesn't make any difference for this aspect. So it was interesting that this natural, generalization of the integers, its H number in the Mathias model was aleph 1, even though the H number for P omega mod fin is aleph 2 in that model. And then a couple of years later, Ottmar Spinos and Saharan proved that the product of n star with itself, the H number drops in the Mathias model. And I probably should have mentioned that Balcar and Simone, I think it was just the two of them, had studied the H number of the finite products, and they showed that it was monotone descending, but they didn't know when and if it could drop. And so they've shown that in the Mathias model, it drops immediately. Very lovely paper, although Ottmar told me he doesn't like it. Okay, so another connection to pseudo-intersections topologically is the idea of converging sequences. So still a major open problem in set theoretic topology is the question of whether or not there exists an Efimov space. And the Efimov space is a compact infinite space that doesn't contain either a converging sequence or a copy of beta n. So whenever we've been able to figure it out, the answer is yes, there is an Efimov space, but it's not known to be independent. So maybe there just is one. And a lot of people would be very interested in that. And my favorite line of attack, you know what, I got the wrong slides here. Oh, I'll have to skip many things, is Koschmidter's T algebras. So I'm gonna have to skip that because of time, but I wanted to mention this result a couple of years ago of mine. Using his T algebras, you can get a model using these the Laver forcings adding diagonalizing. So raising S using Laver forcings, and yet getting enough an Efimov space of character aleph 1. So the splitting number goes up to aleph 2, but the character of every point in this Efimov space is aleph 1. And what that says that because that Efimov beta n will map onto that Efimov space, and you pull pre-images back, you can get a covering of n star by a whole bunch of nowhere dense sets of character omega 1. So all of these sets, let me say that again, a bunch of filters of character aleph 1, none of which have a pseudo intersection, and yet the splitting number is aleph 2. So now that was special in that model. Now that had already been done by Brendle and Shelah. So they had already asked independent, I mean, never mind independently, they had a paper in the transactions where they were studying. So they proved this, right? So using the labor forcing, you know, you strategically choose or construct usually a selective ultrafilter, and you shoot a pseudo-intersection. Selective ultrafilters gives you much more control about what you can preserve, about where you don't want to add pseudo-intersections. And so indeed, that's what they figured out, that they can arrange, you know, through reflection, of course. You reflect an ultrafilter, you keep raising S, but once you've reflected that ultrafilter, you don't add a pseudo-intersection to it. So for any cardinal kappa, regular cardinal kappa, you can get the distinction between the pseudo-intersection number. So that I think Jorg might have, I think Nikos might have defined it, but the first official time I saw it was in this paper. So the pseudo-intersection number of an ultrafilter is the minimum family of members of the ultrafilter such that that family has no pseudo-intersection. So anyway, that was a result. And I've always sort of hinted at this early, been interested ever since Balcar-Simon's result. You know, how can you, even I've been working with Saharan and getting nowhere on trying to distinguish H, B, and S, you know, try to get them all different and H bigger than Aleph 1. Now, Martin and your recent paper where you got H less than B less than S, right? Jorg told me that. But H less than S less than B, I think, is still unknown. So anyway, I was playing around with that. In order to do this, we now want to talk about matrix forcing. So there's no, you know, matrix forcing was introduced by Blas and Shelah. And I think it was named matrix forcing by Jorg, not sure. So what they did was they, well, let me just jump to the next slide. So they use their component parts, they're iterating with this Matthias forcing, adding pseudo-intersection to strategically chosen ultrafilters and just going along. But here's what a matrix looks like. So I stole this from Jorg's presentation at the Winter School years ago, just copied and pasted. So, you know, you have this matrix array of posets. And what you're really doing is just forcing with this top right poset, but the matrix array allows you to factor the poset in a million different ways so that you can prove preservation results. And so a matrix iteration, if I'm not oversimplifying. So, you know, as you go from one column to the next column, you're just, this poset here is simply this poset star some poset here. And the trick is as you go up a chain, everything's supposed to be completely embedded in everything else according to the pictures. But what de facto happens in matrix forcing, if I'm not oversimplifying for experts like Diego, this chain, the chain of these posets as you go up, this guy star Q1, 0, this guy star Q1, this guy star Q2, etc. What's the connection of the Qs as you go up? So they don't have to be an iteration, they just have to be a increasing chain of relative complete embeddability. So this guy doesn't, the Q down on this level doesn't have to be in fact, you don't want it to be completely embedded in this one, but only with respect to Maximani chains that have names by this guy. So that's the nature of matrix iterations. And in one sense that they're simple, is that as you go horizontally, it's just, as you just stick on a row, you're just doing a finite support iteration of CCC posets, but it's how you go up and to the right that's tricky. And you have to be, you know, it's hard to find, I guess you could say, suitable posets to use in the columns. The idea, the tricky part is that you, like Heckler is a great example. So right down here at the bottom, you use the Heckler poset, and you always use the Heckler poset. So it's not an iteration as you go up a column. It can be, that's the easy case. But what it is really is you're just adding more and more and more side conditions. So these posets here are adding new functions from omega to omega, and the Heckler poset is getting more and more commitments. It has to dominate more and more and more. So the Heckler real you add down here, seemingly, the name is down here, but it will dominate the entire model so far. So that's very mind-blowing. I remember being in Jorg's presentation of matrix forcing back in 2014 or something. Very well done presentation, but nevertheless, he lost me. So that's what matrix forcing is, and let's now jump to this generalization. And I believe it might be new to this paper I have with Saharan, because he never said, oh, refer to F4072, but just simply he introduced it for this paper. So, so here comes our main result. And I guess as I said, I somehow got mixed up about which set of slides I'm using. I wanted to generalize Jorg's result here. And it kind of occurred to me to ask this for a couple of different reasons. Never mind that. So could we make this gap? So they got a step of 1. Could you make that gap arbitrarily wide? So that's what I wondered. And whenever you go visit Saharan, you have to have good questions. And I thought, okay, maybe that'll be a good question. Well, I think it was. So we start with a model where you pay arbitrary regular, GCH, an arbitrary regular cardinal kappa, much less than the lambda that you want. You don't really need GCH, but GCH at lambda. You want a non-reflecting stationary set of the stationary subset of lambda consisting of cofinality kappa limits, because we're going to do a kappa lambda array of posets. We want to do a lot of anticipation, so you'll want diamond to hold on that stationary set, and then you'll see why we want square to hold on that stationary set. And what that means is for every alpha for every alpha, you want a club in alpha, and the clubs should always avoid that non-reflecting stationary set, and they should cohere as usual in a club sequence. So that's the hypotheses of the ground model, and before we do our forcing. And so what we prove is there's 2 different CCC posets. Both of them will force the splitting number right up at the top. One of them will force B going up to lambda. The other can allow B to stay at kappa. But the big thing we were working on is every ultrafilter has pseudo-intersection number kappa. Okay, so you could say, okay, so what? Just playing around with forcings, and that's true. But it was interesting techniques. So here, I think, and even I think Saharan agrees, are the interesting aspects of this result. So we're going to generalize matrix forcing. I didn't know what to call it. He didn't say. He just called it a system. So I call it sort of an array of posets rather than a matrix to distinguish it. And so, so I just made up this picture. It's going to look more like a triangle than a matrix. So you'll see what I mean in a second. So that's one interesting aspect of this paper. So maybe this is, surely this is a new method that might give some new tools. And the second was, and I think he also liked this, it's his idea, naturally. So we lay a trap at every limit ordinal, we lay a trap for somehow we have to pick, for every ultrafilter, we have to pick a kappa-sized subset of that ultrafilter and say, there's the kappa-sized set that we're not going to allow a pseudo-intersection for. And so we're laying a trap at every limit ordinal. We say, well, here's a bunch of sets that we might choose from. And then the neat thing is this retroactive, we're way up high. It's at some ordinal less than lambda. We look back and we say, you know what? We should have chosen those guys to be the kappa many that we don't give a pseudo-intersection for. So that's the 2 things that I'm going to highlight as we sketch the ideas. Okay, so the 2 standard features of the method is that we still use we add a whole bunch of Cohen reals, which allows us to construct at every stage, allows us to construct a bunch of selective ultrafilters. And we use this, this using an increasing chain of ultrafilters fits the matrix iteration methodology, the complete embeddings work. And we're going to carry along a notion called thin, which is thin is like roughly like being Cohen over a model. And so we'll have an ideal of sets that we'll call thin, and that'll be our commitment that we will try very hard not to add a pseudo-intersection to those guys. And that's in the model. Using labor adds a dominating real, so that's in the model. Adding dominating reals, getting B equal to lambda. And to get B staying small using kappa, we'll use this variation of, Saharan calls it his Q Boulder. So the Boulder proceedings where he first proved that the bounding number can be less than the almost disjointness number and the splitting number. And if you mind, personal note, years and years ago, not that many years ago, because Vera was still a PhD student, I remember Juris telling me Vera's brilliant idea of extracting a CCC poset out of, and so we'll use that. So that's a CCC poset that allows us to add a pseudo-intersection and allows us to preserve an unbounded family. And now in each case, we're going to be choosing a large family of sets that will somehow contribute to not adding pseudo-intersections. So, and now what that is, okay, so our families will be much bigger than that, but it goes back to the original Shelah paper, which was matrix forcing, and their family was just simply for every, so the alphas is the horizontal and the i's are the vertical, and simply at height I in the very first column, you add a Cohen real, and so the families from then on are just simply those guys. They commit to not adding a dominating real over those Cohen reals, and we instead commit to not adding pseudo-intersections. So that's this somewhat standard ideas, although this idea is going to be more general. All right, so just to set it up, let's give a name to names. So what are the names? I think I put it in. I had a picture. Oh, okay. Unfortunately, I don't have a picture anymore. I got the wrong set of slides on. Stupid of me. Yes, okay. Well, you know what? I can go back to Jorg's picture. All I did was draw on top of Jorg's picture. So a point. What's the difference? Well, we still have this array of posets, still an array. But all we'll do is we'll say, so in matrix forcing, you demand that absolutely every pair of columns, this guy is completely embedded in that guy. And so that's the strong demand you have on the coherence. And so we weaken that, where just given any two columns, you have to eventually cohere from some point onwards. So from some height onwards. So column 0 and 2, you say, okay, when I get to column row number, omega plus 9, from then on, this is completely embedded in that. So given any two columns, there has to be a height that from then on, you have to have the coherence, the complete embeddability. So that was the picture I was going to draw. And the picture gets interesting when you're at, suppose, lambda. And by the way, also, you don't have to have a right-hand column because that's going to be problematic, whether or not. So in a matrix iteration, your right-hand column is automatic. If you're at a limit ordinal, you just take the iteration along the rows, and that's what your poset is. But here, that's not true. So what we can do here is, so as my picture was going to show you, if the cofinality of lambda was equal to mu, then you would kind of have a diagonal situation where you're taking your time about when you're demanding coherence. So that would have been the very, very nice picture I had drawn.
I have a question.
Yeah.
In this sort of correctness condition that you get,
yeah.
what is left over from that then? I mean, if I take a sort of square in this? Do I have some sort of?
But you just have no demand that this guy is completely embedded in that guy, right? This guy is completely embedded in that guy. This guy is completely embedded in that guy. And this guy, was, I guess the way to think of it is you're really defining the top row. That's what you're really defining. You're defining this guy. And he's the finite support union of the entire top column. And so even when we get to lambda, we don't have a right-hand column. We only have the top. So we're going to have columns all the way up, but not a column at lambda. And as I said, the coherence takes its time before you can.
Just the names, I mean, the way that you described it before, I really like it. Sort of saying that you have the name sort of zero alpha.
Yeah, you have that concept there.
Right. And that name is still there, that whole part.
Yeah, that's right. Everything's still there. It's just what's the relationship between those. Yeah.
But in the limit statement for lambda, you also have this problem.
Yes, yeah. You have a problem everywhere other than cofinality less than mu. Yeah. It turns out there's no obvious way how to extend. Yeah. So that's where square comes in. So syntactically, the coherence conditions are this is as you're going up a column. This is a continuous increasing chain, continuous at limits of uncountable cofinality because we want to keep CCC. Everybody's CCC, and then here's this given two columns, alpha less than beta. There's an I, so that from then on, the left guy is completely embedded in the right guy, and you just don't care what happens below that level between those two columns. So that's why I think like the triangle, although the triangle really only is the right picture when you're at cofinality. I'm using kappa at the top. When you have a beta of cofinality kappa, it's probably going to look like this, right? Where you don't really, you never completely cohere. You just getting closer and closer and closer. But nevertheless, the top of this column is completely embedded in the top of that column.
Iota alpha.
Where you decide to commit. Yeah, that's right. That's right. Okay, and then the top, it follows from the definitions. The top is a continuous increasing chain, and so the guy you force with is the top right-hand corner, and the rest, of course, just like with matrix forcing, is just so you can say I got all these completely embedded subhost sets, and I can trap names, and I can make assumptions. As I said, I wrote there's no guarantee if cofinality is kappa that you can form the next column. I should have said if cofinality is bigger than or equal to kappa, there's no guarantee you can form the next column. And so that's why we had assumed square. And so then I'm probably running low on time. So all we do is we just make sure we just keep it really, really continuous along the square, right? So just take just unions along the limit points, the usual deal for a square sequence. And a technical reason, remember I'm laying a trap at successors of limits. I'll also include the commitment. So, and the commitment as to when you cohere is right at the bottom between for those squares. And that allows you to get the, so you concentrate on successor steps and then limit steps take care of themselves, like it does with matrix forcing. Okay, so here, so in the 2 minutes remaining, I guess I'll tell you about the trap. So here is a really clever idea. So so every once in a while, every successor of a limit for no loss of generality, here we lay a trap. So we do a very simple forcing. We just add an uncountable size omega 1 almost disjoint family of subsets of omega with finite conditions, which of course ends up being a maximal almost disjoint family by genericity, but it doesn't even matter. So that's what we do at the successor right down at the bottom. And also we enhance the structure. I guess maybe I'm running out of time. I know I'm running out of time. All right, so so we're carrying along these commitments. So these commitments are they're sitting at a height I, and the commitment is that no name with support below I can be a pseudo-intersection to anybody. So none of these guys, can there be a name with support below I that is mod finite contained in any one of those guys? Does that make sense? And so we want to keep adding to this family, but we don't add anybody, but here's where we're laying the trap. So we add the almost disjoint family, and the trap is the complements of the almost disjoint family. So this family of complements has the property that the union of any two is omega. So you, and if you're trying to make sure this ideal generated by this guy can't have any pseudo intersections, it's not going to work. You can't add any more than one of these guys to your commitment. And so what we do when we spring the trap is we use diamond at members of the non-stationary, of the stationary set. And we say, well, you know what, suppose we've trapped an ultrafilter. And now we look back and we don't want to find conditions that decide this or that or that. We look back, you have this omega-1 size family, the ultrafilter cannot contain more than one of the complements, right? So if you have an ultrafilter, you cannot have an element any more than one of those almost disjoint members. So one forces there is an ordinal below omega-1 that the ultrafilter does contain that guy. I'll say that again. So the one forces that there's an upper bound on the members of the almost disjoint families that the ultrafilter could possibly contain. And so we can choose a suitably big C so that one forces that guy is not in the ultrafilter, and then at stage mu, we go up the column at stage mu, and for each I, we add this guy, and that's it. So that works. Okay, and I had one more paper with a result using this method, but that's quite okay. I'll stop there.
We already had a discussion, so yeah, I mean, it's fine that you took 2 minutes more.
No,
but, I mean, I was actually going to ask like what you can do with this Bossinger, like. What, I mean, if you can see any other applications, for example, for this method?
I just had one other one, which probably I'd like to raise this question. A really silly one. Again, I had to have something to ask Sauron. So I came up with this question. So I'm motivated by how big a difference can you get into it. I'm still working on trying to get H less than S. And it was my paper with Sauron on getting S singular had a method in there that reminded me. So here's a strange thing, which I thought the answer would be no, it's impossible. Can you have a family? Think of these as mutually generic column-reals to start with. So you got this family. This family should be eventually splitting. So the split and the splitting number should be S. So every real is from some point on. Every member of that family splits the real, and yet going back to pseudo-intersections. So, but notice the splitting number is lambda. So many things have pseudo-intersections. And think of this as an independent family. So you got all these filters you can form from that independent family. And yet they're trying to be very prescriptive as to which things can get pseudo-intersections. So they have positive, negative choices to give a pseudo-intersection. And that is what happened in this paper. Positive, negative choices. And I'm just saying that you always have to choose negative. So no kappa-sized subset of this family can have a pseudo-intersection. So is that possible? Can you have kappa less than lambda with this property? And if so, how big of a gap can you be? And why I dreamt of this is because of a game approach to splitting, getting H less than S. And so with this methodology, I could get a gap of 1. I could get kappa and lambda equal kappa plus. It seems a very weird property, but